This is the last lecture on precise quantum measurement that we can call quantum metrology. Why metrology? Because that's the part of sciences that deals with precise measurement, right? Metrology is to measure and to measure really accurately. And as you know, basically all countries have the institutes that deal with that, and how to measure all possible physical parameters. And high resolution. And of course, if you know how to measure it accurately, you can make sensors, and that's where it becomes useful for some purposes. Well, I'll talk about the introduction of this. I'll talk about, in terms of quantum measurement. It's entangled photon interferometry with high phase shift resolution. For the first one, quantum optical measurement, quantum metrology, you not always need entanglement. Sometimes just non-classical optical states is enough. But if you have entangled photons, you can have some extra additional features that you can use, and I'll show you that. Well, then we can talk about interference is one of the basic tools of metrology, of measurement, right? Interferometric measurements, because it allows you to measure very accurately phase shifts. So we discussed what it depends on and what are the modern ways of improving the sensitivity and resolution of such measurements, including some elements of quantum interferometry that is used like in gravitational wave detectors and many others using squeeze states, not only entangled states, but squeeze states of light as well. And then the last piece of this, I will show you something that you probably have not seen before. This is my personal latest research that I like very much, because one big thing today in quantum optics is lots of people doing that. There are not too many new, fresh ideas in the area. And we were lucky to find some, and I'll show you some interesting applications of that, how the interferometry and sensing can be modified, and what else you can do in terms of quantum networking, distribution of quantum entangled states with that. All right, so, lots of developments in quantum optics first of all, quantum optics is not so old. It's, the beginning of quantum optics considered to be in the 50s, after the Henry Brown Twist experiment. So the first experiment where the correlation between single photons had been used for something. So basically measuring correlation, joint correlation between two single photons, which means you have one detector of single photons, second detector of the single photon, and correlation is measured by the coincidences between electrical pulses from the detectors. But later on, things start to develop. By the way, Len Mendel, when I was a student, I learned about his work from his famous paper from 1958 about the statistics of photoelectron counting. So if you have a photodetector and the photons are coming in, and you detect them, and you detect the statistics of photoelectron pulses, the formula tells you how the statistics of the light coming in and statistics of photoelectron pulses are related through the parameters of your detector. So basically, there was a limitation on the parameter of the detector if you want to learn statistics of the light. Because if your detector is too slow, you may not be able to get the statistics of the light. But then Len Mendel came into the quantum optics from this area, and that was one of the first experiments with correlated states of photons. And the interesting thing is, this is gave a big kick to the whole quantum optics development area, and you can see that the title It says a measurement of sub-picosecond time intervals between two photons by interference. It's metrology. It's a first quantum metrology example. So the idea was that you have a source of single photons, and we'll talk more about this. They come to the beam splitter when these distances are absolutely the same and these photons are indistinguishable. You're not going to have any coincidences between these two detectors. When you start to move the beam splitter, you move it one way, so this arm becomes a little bit longer than that one, so there is a degree of distinguishability. And this forms the dip into the graph where here on the horizontal axis is the position, so it's a delay between left and right, and degree of distinguishability of arrival, and on the vertical axis is the rate of coincidences. By the way, when you talk about, look at all the data on coincidences, always pay attention to the rate. This is number of coincidences counts in 10 minutes. So they are not very often were coming at that time. So to get these statistics, you really have to wait 10 minutes at every single point to detect it. Okay, so what this is about, so you have a beam splitter. Beam splitter, it's a well-known device in optics. So you have one field coming in, you look in one. This is second mode. It's a four-mode device, first of all, four mode. One in, second in, and one out, second out. This beam splitter has a particular matrix associated with transformation of electromagnetic fields. It's a 2x2 matrix. The specific formulation of that matrix could vary, but it depends on what material and how this beam splitter is made of. You know, the beam splitter could be just piece of glass, just simple piece of glass. It could be two prisms, like here, right? It could be two prisms with the air gap, or two prisms with some material inside there. And many other ways of, like, it could be piece of glass with multi-layered dielectric coating on one side or on the other side, and based on that, the phases are different, but it's always kind of almost the same. So then, as we said, so there are four modes. Remember yesterday we discussed modes. Modes are classical things, right? So what's quantum is when you start to put energy in those modes. This A dagger 1, A dagger 2. So it means one photon in the mode 1 and one photon in the mode 2, here and there. And they both come in. And then you ask yourself what's the relationship between these two and between the output modes. Each output mode is a superposition of these two, right? Because this mode can have part of here and part of there. This and this. And then that one could be this and that, superposition of two as well. And then you can calculate what is this total state. You just take this, just multiply them all, and you discover that because of the particular matrix of the beam splitter, the cross terms will be gone. You will be one photon in the mode 1, one photon in the mode 1, which means two photons in the mode 1, or, because this is one state, this is second state, or two photons in the mode 2. You can write them down as 2, 0, 0, 2. 2 in one, nothing there, 0 there, nothing there, and 2 in the other one. So this factor doesn't matter because it's called the global phase. What matters is the phase between these two terms. This phase doesn't matter because this is still at the level of amplitudes. When you go to observables, observables will be intensity. Intensity is the product of these two. So this one times its complex conjugate, and this phase will disappear. That's what matters that will be there. So it tells you that you put 1 and 1, but you will have 2 nothing or 2 here and nothing there. So that's the essence of the Heisenberg effect that comes from the interference of amplitudes. You see, that's why it's quantum, because it happens at the level of amplitude. That's where quantum mechanics operates. We discussed it yesterday, what the difference between classical entanglement and quantum entanglement. Quantum entanglement for the amplitudes and phases. That's what it is. And it's called the photon bunching sometimes. So two here, they kind of got stick to each other, either here or there. And of course, if you put here detector and here and try to make coincidences, when two goes here and nothing there, there's no coincidences because there's no energy going in that channel, nothing to show up for the coincidence circuit. Okay? And or it's, we call the Hong or Mandel dip when they are perfectly indistinguishable. You see, this is the indistinguishability in here. If by any chance this term starts to get distinguished from this one, like by time of arrival of the photons or by any other means, then you will be on the, you will be going right here, here on the shoulder of this curve. That's an increased degree of distinguishability. Now they're fully distinguishable, so there is no modulation. Quantum effect is gone. Quantum interference is gone when they're fully distinguishable. All right, what is good for? Well, to measure sub-picosecond intervals, yes. What the accuracy of the measurement? Well, I mean, you put some material, and the accuracy depends on how broad is this curve, right? This curve is defined by the wave packet of the photons. So you have to ask yourself where they're coming from. If it's coming from parametric down conversion, like as in his paper, regionally, so this is defined by the phase matching condition inside one linear crystal, basically this size. Usually it's hundreds of femtoseconds. And when you look here, so what is the full width half maximum? That's about like about 100. No 100, it's even less than here, right? So, oh, it's in microns already. It's converted into microns. So it's several hundred femtoseconds converted in microns. Because you see the microns and seconds, they are connected, right? The connection between them is speed of light, right? So it's, any experimentalist knows that 30 centimeters in free space is 1 nanosecond. That's your. If you remember that, then you can also go to picosecond, to microns, whatever. 30 centimeters is in free space. If you go inside the material, you have to divide it by the diffractive index. Okay. Well, one very good use of this is measure of distinguishability. Because, as you see, so the full dip going down to 0 is when you have fully indistinguishable photons. In fact, one of the areas where it happens to be very, very, very useful is the area of the quantum dots research. Because I mentioned to you that for a number of applications from quantum communications and other, the holy grail of quantum optics is the so-called single photon gun. So a system that you push the button and send you a photon of desired parameter at this time, or this frequency, for example. So, and why it's holy grail? Because if you have two of this, then you can push the button, you send them, and you have two fully correlated photons. Then you put superposition between them on the disk, you have entanglement. So basically, for quantum communication, you push the button and you have one photon going, and you can encode it with polarization, or sometimes even quantum dot can have internal encoding, so it will spit randomly. You push button, it will be one polarization and another polarization coming out. And of course, you would like to push this button as frequently as possible. So, but the problem is not in speed of the kind of thing. The main problem is indistinguishability of quantum dots. Because what are the quantum dots? Quantum dots are artificial atoms, basically, right? Dot, quantum. Which means you have something, there's matrix of something, and then there's a dot, tiny thing that is different. And because of it's different, it's sitting in the environment. When you do the quantization, you will come up with some energy level structure that is quantum because it's microscopic. But it resembles that. But it's in the environment, so environment affects the distribution of those atoms, of those levels. So, and as a result, they always slightly different in different because they come to different places. And so this is the issue with quantum dot community. First, where the quantum dot is. Again, they're also very random distributed. You have to find them. And then it's impossible to find two of them with exactly the same parameters. And still people searching to improve the degree of control on making such things and how you test it, how you verify they are same or not. That's exactly what you do on the man of dip. Because you have two photons coming in, you fire them simultaneously, they come to the beam splitter, you measure, and you have like this visibility, this visibility, this visibility. As you can see, it's pretty far away from 100%, but not so much far. So this is 0.5, like in this one. So you have to work more on indistinguishability of these photons to get this to the bottom. The other thing is, from the width of this, you can say, oh, what was the spectral width of that? The bandwidth. Because wave packet and bandwidth, so delta omega and delta t. This is the delta t, nanosecond, you see. From here, you can calculate the spectrum of your light. And you know, for some applications, you need narrow band. For some applications, you need broader. So that's what all the information we get out of here. So it's basically universal tool for testing the indistinguishability of photons. Well, let's see, interferometry. So if you have, it's all based on beam splitter. If you have a regular beam splitter and one photon comes here, nothing here, it's a classical configuration. What you have this 1001, because when one photon comes here, it can go either here or there. Well, that's fine. It's, if you take the second beam splitter and make the interferometer out of this, it will be normal Mach-Zehnder interferometer. Okay, if somehow we have access to non-classical state, but the state 1,1 that is used for the Hongo-Mandel experiment, it's a non-classical state. Try to find it. Nature doesn't give you 1 and 1. It gives you 1, 1 and many other things. It's all mixed together, right? So because nature gives you either coherent state or thermal state, that's all what you have. Basically, there are no more options. There is no correlations more than the thermal correlations. To get this 1 and 1, you have to work on it. Like you have to have 2 photon guns with indistinguishable photons, or you have to have parametric down conversion that gives you naturally 2 indistinguishable photons. Okay, then you can have this state 2002. What if you put 2 photons here and 2 photons there? Well, the state becomes more complex because you have more options here. Why? Because beam splitter is really a non-discriminant element. It doesn't know how many photons will go through and how many will go reflected. There's more combination. It's like nothing goes through, 1 goes through, or 2 go through. That's 3 options from one side. And then the same from the other, you combine them all together, and that's what you will have. It's a big mess. It's not a clean state. Well, I've shown you what you can do with entangled photons. So if you do the entangled photons in the collinear configuration, remember I showed you instead of the non-collinear one, you put it in one direction here, and then put beam splitter, these 2 lines, 2 detectors, and coincidence circuit. That this configuration cancels the unwanted terms. And basically, you would have it here as if you have entangled state coming in. And when you try to do the coincidences versus delay, here delay between 2 photons, these 2 photons are having 2 opposite polarizations, one horizontal and one vertical here. And you put birefringent delays, it's just 2 crystal quartz wedges. When you move one wedge relative to the other, the total distance here is changing. and it means you move it along this axis here. You introduce degree of distinguishability between H and B. When they are absolutely indistinguishable, you are here at 0. To some extent, this is the polarization counterpart of the Conventional Interferometer. That's what it is. This is in space, this is in polarization. Well, in practical interferometry, if you've ever done that, you know that polarization interferometers are usually substantially more stable, because this is only one path and stability of photons on one path rather than to keep this spatial structure. Just try to stabilize the regular Mach-Zehnder interferometer on the optical table, and you will see what it is. Here it's much more stable, but works the same way. So this is indistinguishable. That's a cancellation of amplitudes, because remember, if you put entangled states here, remember at 45 minus 45, no coincidences. At 45, 45, maximum coincidences. So basically that's what it is. But then if you introduce here a sample, some sample, like piece of fiber, then you would see that your dip will be shifting. So this shift is directly proportional to the difference delay between these two polarizations going through the sample. So you can measure birefringence of the sample. And so the shift in dips is a measurement of birefringence, similar to the complement of sub-picosecond delays. You see, it's femtoseconds per millimeter. So it's in the same range. Again, the accuracy of the measurement depends on the width of the dip, and that's what it is. That was the first application, or first entangled photon interference. Because it's in coincidences, it's much more stable than any regular Mach-Zehnder interferometry. It's less sensitive to noise. Its signal-to-noise ratio substantially higher. But of course, you have to pay the price. You have to make this state. You have to deliver a line and everything else. So that's basically, that was the first apparatus that Mette Atatürk built in the lab. That was his first experiments in my lab. Well, then there is another very interesting thing is, what if you take the Mach-Zehnder, but then you introduce this delay right here, which means on this apparatus, it's take the delay line from the front, put it in one of the arms. What's interesting about that? Here it becomes like you have two photons. One photon comes here and gets detected. Second photon comes here, gets delayed and detected, and then coincidences. And then you can see the modulation of the interference with delay. But this photon never sees the delay. Why the joint result is modulated is because the state here is still the same. It's still the same state, HV minus VH. So it just highlights the issue that the state propagating in these two directions is the same state. It doesn't matter how far away you move this and that, it still will be the same state. If you disturb it here, you disturb the whole quantum state. In classical physics, you disturb it here, then you didn't disturb the other one. In quantum mechanics, whenever you have a good state, a good quantum state, entangled state here is disturbed. And what you can have is this. You have an envelope like before, but there's also internal structure. In interferometry, radio interferometry, you know, so there's two things. There is the envelope of interference pattern and the central fringes. Envelopes are usually associated with the group velocity delay, and internal one with the phase delay. So traditionally, in the measurement in metrology, when you want to measure accurately phase delay, what you do? You have to have an interferometer, and you have to have a monochromatic light, right? You have a nice, clean sinusoidal signal, one single frequency. And then you put a phase delay, and your picture shifts, right? And you just count how much it shifts. the more monochromatic light you have, the better you can measure the phase delay. If by any chance you have to measure the group velocity delay, like propagation delay, right? You have to use something else. You have to use the envelope. Because like when you, for example, if you delayed by, if you have a high visibility interference for the phase measurement, and then you move it by 200 fringes. It's very hard to measure that. Like you put sample and suddenly you see the same high visibility fringes, but they were moved, and you don't know for how many. For that purpose, you have to use the envelope here, and this is the group delay. However, to measure the group delay more accurately, you have to make sure that this envelope is not very broad, because resolution depends on this, on the derivative, how accurately you can find this point here. If you have it like broad as that, you can locate it with less accuracy than in this case. And this is the coherence time. The smaller coherence time, to get small coherence time, what do you need? Large bandwidth, right? The larger the bandwidth, the smaller the coherence time, because there are two Fourier conjugate components. So if you have a very, very broad wave packet, then you can have very narrow interference pattern here in the narrow envelope. This is called the white light interferometry. You may have heard about it. So to get high resolution measurement of the group delay, you need to have a broadband light. This is classical approach to interferometry. So to have a high resolution phase measurement, you need narrow band source and interferometer. To have a high resolution group delay measurement, you need to have a very broadband light and interferometer. Same interferometer, Heisenberg, for example. Okay, so that's classical. The beauty of the quantum thing here is that in one single measurement, we can do both of them. Phase and group. Why we can do that? Well, because we use completely different principles and different technologies. That is more complex than classical. Classical is just source interferometer done. Here is the source is a 2-photon entangled state in particular arrangement of delay lines and polarizations of detectors and coincidences. The main parameter is coincidences. Okay, so what a regular interferometer is based on light count interferometer, detector measures intensity. And you measure what intensity is going up and down, right? So intensity is the second order in electric field. It's E squared. Here we're measuring the coincidence between two intensities, because each detector signal is directly proportional to intensity. Square of the field, square of the field. So it's a fourth order of the field, or intensity times intensity. It's intensity correlation. So we are moving from the second order to the fourth order correlation in the field, and that's why we can do the group and phase velocity simultaneously in one experiment. Well, what kind of benefits also we have in comparison with the with conventional interferometry in this case? Well, let's say we would like to measure the group delay. We need to have a wave packet, white light interferometry wave packet. So here's the delay. So check it out. So it's like 160, 170, basically full width half maximum here is 10 femtoseconds. So try to get this interference pattern with the conventional laser. So which means your laser has to be at the order of 10 femtoseconds. Actually, it has to be shorter to get this. Basically, you know the theory of autocorrelation of laser pulses, for example. Okay, so to get a 10 femtosecond laser pulse, have you ever seen the laser that gives you 10 femtoseconds? How big it is?
Size of the room?
Not room, but it's substantial. Well, nowadays it's smaller than before, but it's still, it's not an easy job to get 10 femtosecond pulse. Here it's just, it could be a diode laser and a piece of crystal, that's it. and you get the interferogram with the wave packet that gives you easily 10 femtosecond bandwidth. So because of that, you can measure much more accurately the shifts, right? So with 10 femtoseconds, when you start moving, you can calculate the slope here and accuracy of evaluating the bottom. What's more interesting here? So the internal structure. And the internal structure is defined by the wavelengths of the light you are using. In fact, it's about like 1 femtosecond here. So, and the visibility of this is very high, as you can see. And the most interesting thing is that there is a possibility in quantum entanglement interferometer to arrange such that the envelope and internal structure, they will be locked to each other. So not only you can measure both of them in one experiment, in contrast to classical one, you can also arrange them to be locked together. So if you lock them together, make sure that in the center of this envelope you have destructive interference right here. So you can identify the center, because that's what really a measure of the delay usually, how much this center from the other center when you change parameters. So the center of this envelope of like 10 femtosecond envelope can be identified with the resolution of the central fringe that is 1 femtosecond. So you kind of project the phase measurement accuracy onto the group delay accuracy. Because conventionally in white light interferometry you cannot get this resolution that is from the phase interferometry, because broadband source cannot give you this envelope resolution. Okay, that's what it is. It was just a demo experiment. So this is one, this is second one, and basically this is all femtosecond scale. And as I told you, you can have this central fringe that helps you to identify the distance between these two centers. This D is the difference of group velocities times the L of the sample. So you measure the difference between group velocities of ordinary extraordinary wave inside the sample of the length L with sub-femtosecond resolution. Why sub-femtosecond? Because the whole fringe here is 1 femtosecond. The displacement can be measured to the portion of that fringe. So in fact, you can go like to about like 10 attosecond. Usually they say that in metrology, so if you have a fringe, how well you can resolve position on the fringe. This always depends on first on the slope, how sharp it is, or in our case it's basically full fringe is 1 femtosecond, and then visibility. The higher the visibility, when visibility goes down, and the fringe kind of getting slow, slope going low. But you can, like, here you can divide it in 100 pieces. If your visibility is like 50%, you only can divide it in 50 pieces. All right, so what it leads to, also, there is a very, remember I told you the interesting thing about frequency entanglement and primary ground conversion. So entanglement is superposition and correlation. Remember, HV, VH, long, short in phases, for example. This is the same is true for the frequencies. It's plus delta, minus delta, plus delta. So omega 1, omega, like omega plus, minus, plus. So shift from the center. And this internal structure exists only in correlations, in coincidences, and only because the original pump is not fluctuating, basically. It's a highly narrow laser. Like you take the very, very narrow band laser, send it to the crystal. The crystal, through the phase matching, gives you distribution of signal and idler. But inside that signal and idler, you can always pick up one component here and you can find the fully correlated component on the other side, and vice versa. So this frequency entanglement leads to the interesting situation that is called the even order dispersion cancellation. So you can basically, you see like omega minus, or plus here, the merit minus plus. So omega minus, omega. Mine is relative to the center of the wave packet. And basically this is like omega pump equals to this plus this is signal, this is idle. Well, the phase shift, as we all know, it's omega dependent things. Basically the delta omega can be represented as in the Taylor series, like k is a function of omega. What is the first order, zero order of the k of the omega? Who knows the optics? So remember the k of the first order is linear term. This is already first derivative. So the first one is just omega over k. What is it? It's a refractive index, basically, right? Phase velocity is how much smaller the speed of light is. A refractive index. The first derivative, it's a group delay. What is the second derivative? Dispersion of group delay, which is the particular coefficient, second order derivative, the one that tells you how your wave packet broadens when you go inside the material, right? Okay, so one can show there's like very simple math that if you go to the situation of this situation, so if you measure this and if you do the conventional interferometry, then the basically this is corresponding to, this is 0 and then it's a longer sample. You change the sample length. The longer the sample, you see the broader the wave packet becomes and the visibility becomes lower. That's a fact of the second order dispersion. When you cancel second order dispersion in this combination, well, it only happens here. When you have a frequency entangled state, you have two detectors and coincidence detection. One can show that instead of this, you will have, well, first of all, the shape will be triangular. And then the shape doesn't change when you move it through by introducing the sample. Well, why do you think the shape is triangular here? Conventionally, all the wave packets are Gaussian, right? But here the shape is triangular. In fact, we verified this very early enough in experiments. There was a joke even about usually when you have a Gaussian wave packet in the correlator, you just move it one through the other one, you have a correlation function, and it will be Gaussian, right? Here you have a square, or like you have, when you observe an experiment, this triangular shape, you ask yourself, what was the shape of the photon that you were moving? To get triangular shape, you need two rectangulars moving like this to get a triangle, right? So you have square photons going around. Well, of course, in reality, it's not. Photons have squares. It's a probability of photons to be born inside material and acquire some delay. They're based on where they were born inside the material. And material is a crystal. Crystal has a length. And the process is spontaneous, so the equal probability of coming from anywhere, the probability is the square. Probability amplitude, and then you square the probability amplitude, you have a probability square. Anyway, so that's kind of very interesting thing. You can remove the broadening of the wave packet from the consideration, and basically that would be the net result. In conventional interferometry, to get as good as possible group delay resolution, you have to put as broad spectrum as possible here. When you have broad spectrum going in the object, you experience more dispersion. The broader the spectrum, the greater is the dispersion. And then your envelope is spreading. and you reduce accuracy of measuring of the center of this. When you have quantum case with even order dispersion cancellation, then you put this one and it goes, it's exactly the same one, so you do not lose the accuracy in evaluating the center. You just have to make very broadband light, entangled light broadband to obtain this triangular as narrow as possible. So that's another area of research and has been done many times. The other interesting, the last thing is, remember I told you, it's effect of the dispersion cancellation. Dispersion cancellation is for even orders. What are even orders? Second is even, right? Fourth is even, right? But their fourth already a very small contribution. How about the zeroth order? Phase delay. It's also kind of even orders, right? The first one is a group delay. Group delay you cannot cancel because if your light travels through something, there is a delay associated with that. But zero you can. So basically what you can do, you can have a sample introduced here, and when you change the length of this sample, you will have interference either here or there, but the shape stays. But the other thing is, look at the internal structure. It doesn't move. The phase is not changing. It's like you have those envelopes moving along the well-fixed ruler of phase velocity that can be used as the ruler to measure the position of the triangular shapes. So you impose the accuracy of the phase measurement through the small fringe to the position of the group delay envelope of the signal. So that's basically two things at the same time due to the dispersion cancellation effect, and basically that's one of the advantages of interferometry with entangled states. It has been done for some, we measured this for telecommunication switches. At that time, the polarization mode dispersion was the big problem with telecommunications. And these days, they really they say, oh, we will fix it using digital signal processing and compensation. But at every node, you have to keep in mind about how they fix it. They introduce some delays using electronic things within transistors. The question is, how many transistors do you have to keep at each node to compensate? So you have to anticipate how many delays will be coming your way. And how much delay will come depends on how your signal will be routed through the network. When you have fibers, for fibers it's pretty simple to evaluate the delay because they're usually big. But when you go to switches, at every node there is telecommunication switch, and each switch can give you delay, either positive or negative, depends on the structure of the switch, and it's relatively small. And the company who was trying to do that, they said, well, we try to measure, we make telecom switches. We try to measure delays. We use the conventional telecom equipment. We try to measure it. They come with the same number, 150 femtosecond, always. Which means delay is there, but it's smaller than the resolution of the device. And they ask us, can you see that smaller than 150 femtosecond? We tried, and yeah, we characterized, and we got some different numbers, plus, minus, 15, 20, but we said, we never seen any delay greater than 50 femtosecond. For them, it means, okay, from 150 to 50, 3 times, which means they can say, okay, you have to have, for our switches to be installed in your network at every node, you have to have particular amount of delay compensation reserved. but it will be 3 times less than if you use conventional equipment to characterize that. So that was a real kind of real estate improvement for that. So that's what it is, and there's more interesting things about the metrology, imaging, communication, if you want to learn. So the better interferometry. What else you can do in addition to entanglement? Well, this is conventional horizontal interferometer, and so the accuracy of evaluating the modulation of the phase is proportional to 1 over square root of n, where n is the number of photons, average number of photons used for this measurement. How come? Well, we all know that here's the delta E, delta T is h bar. We all know it's uncertainty relationship, right? So the E energy is h omega times n, where n is the number of photons, then delta E, h delta n omega. Phi phase shift is omega times t, delta phi is omega delta t. So you put it all together, it will be delta m times delta phi about 1. So this and this, it's the same thing, basically here. So then delta phi is 1 divided by delta n, right? That's what it is. So what is delta n? Delta n is, well, the best classical state you can have. It's called the coherent state. In the coherent state, delta n equals square root of n. That's the property of the coherent state. So then delta phi is directly proportional, is proportional to 1 over delta n, when delta n is square root of n. So that's what it is. Delta phi is 1 over square root of n. That's the definition of the maximum resolution of conventional interferometry. You may have heard about this. So for coherent state, that's what it is. What is a coherent state? Coherent state is the state that people call it, sometimes they say this is quantum state, some people say it's classical state. In reality, it is kind of position at the borderline between classical and quantum. Because coherent state is a state where the photons have Poisson statistics, and it means absolutely uncorrelated. If you go on one side of that, it will be going towards the thermal states with the thermal statistics, Gaussian statistics. Or on the other side, and the other side is the quantum side. What effects do we know on the quantum side? It's squeezing. Squeezing means you run your light through a particular process that reduces the variability here, variation along one axis in comparison to the coherent state. That's what the squeezing is about. And of course, because of the conservation of energy, the variability in the opposite quadrature, of the opposite direction here, is increasing. So you decrease in here, increase in there. For example, here, this is the state. This is the magnitude of the state, which is associated with the intensity. It's a number of photons. So this one, it's a phase. It's the position of this. This vector is rotating, so position of the vector associated with the phase. Magnitude and phase. Phase is perpendicular, magnitude is the size of phase. So squeezing in this particular case, it's, you see, you're squeezing it within the number of phase and unsqueezing kind of in the number of photons. If you do this opposite and you squeeze it in this direction, then it will be like rotated 90 degrees. There will be uncertain in phase, but very, very certain in a number of photons, because this like becomes like very, very kind of narrow circle around here. This is the Fock state of the fixed number of photons. So it could be delta n equals to n. So this one is okay. In this particular case, we're squeezing in this direction. So this size of the ellipse will get bigger, bigger, bigger. So when the ellipse occupies the whole thing here, then it's delta n equals n. It means it will be squeezed in this direction and very narrow in the perpendicular direction. And narrow in the perpendicular direction means very small uncertainty in delta phi. You see? So that's really what goes beyond the, when delta n equals n, this is the Fock state, and when it's true, then your delta phi will be 1 divided by n, not square root of n, but n. And this can only happen when it's extremely strongly squeezed here. So the extremely non-classical state. It's different from entanglement. It's an effect of squeezing is a separate effect in quantum optics. So, that's what it is. It's called the Heisenberg limit. Why it's so good? Because the interferometry is designed to measure the phase change. And this is exactly what you get improvement. You improve instead of the 1 over square root of n, now you have 1 over n measurement in the in your interferometer. The problem is how to ensure that what you put inside the interferometer has n photons going through each part. This is the problem. Because when you go through the beam splitter, remember the beam splitter is indiscriminate device. You create your state here, they call n photons state, but this one mixes it up dramatically. So it's still interesting question how to do that. The only what you can do it for 2 photons. And for 2 photons, let's see. Okay, before, yeah, we'll talk more about this. So this is the how to improve the resolution of your interferometric measurements due to reduction of noise. Because what is this envelope? It's uncertainty. So this is uncertainty in the n. This is uncertainty perpendicular in the delta phi. Okay. This way, by squeezing, we improve in this versus this. So this was big uncertainty, this one is much smaller uncertainty. So our interference measurement could be better. This is improvement of noise. What else defines the accuracy or resolution of interferometry? Well, if you have a regular interferometer here, so this is the interferometric fringe. So how well you can resolve this delta phi. Well, so we already discussed that delta phi depends on the noise. So noise, it really tells you how wide, how broad this line is, right? Because it's not thin line, it's with the noise, delta phi, and we already know how to improve the thickness, to make it thinner. Now, after we made it thinner, what else we can do to improve the resolution? The resolution depends on the slope here. You see, there's delta phi and delta m here. So think about this. This is the one slope, really here, right? And this is the second slope. You see, it's increased. So your measurement is this. This is your intensity modulation, what you measure with the detector in response to the phase measurement. So the sharper is the slope, the smaller values can give you the same change in intensity. That's a sensitivity resolution of the measurement. So how can we increase the slope? In classical physics, how we can increase the slope in the interferometer? Change the wavelength. That's why all the high resolution interferometric techniques go in more and more into ultraviolet, right? That's where you have, you change the wavelengths 5 times, and you have 5 times greater slope here. Can you do something more? There is a nice theory about the Nun state. It's entangled states of n0 plus minus 0n. And it's due to Jonathan Darwin, who introduced them. He was a great guy. Unfortunately, he died several years ago. He was really, really good on inventing some fancy abbreviations or terms, really. So, because it's N00N, it's noon. He even said it was a high noon. There was a famous Western movie, High Noon. So high noon is when the N is large, basically. So what does it mean? It's if you have the operator, like the regular state, it gives you phase shift on the state. When it's n photon, it will give you n times greater phase shift. So it's like amplifying the phase shift, basically. And that's what it is. If this is the original fringe, then this fringe, the green one, will be, so this is for 2 times. So if you have 2 photons, as you see, the periodicity is 2 times greater, and this is for the increase in the, sending the 2002 state inside. Why is it, and this is some literature reference for that. Why I'm saying 2002? Because that's the only case when you can do it, and that has been realized. How it's been realized? So you can have the nonlinear crystal. It sends us 2 correlated photons. This is the first beam splitter. What happens at the first beam splitter, we already know. If these 2 photons arrive to the beam splitter indistinguishable, we'll have this nice Kongo-Mandel dip, right? And in the middle, you see, it's very high quality. It's really like 20 or 02 on both right here, right? Now, we can take this and use it as the, basically this is nothing else than Mach-Zehnder interferometer, right? First beam splitter mirrors, and this, it's a Mach-Zehnder interferometer. So now, Mach-Zehnder interferometer has 2 here and nothing there, or 2 here and nothing there. That's exactly noon state, 2002. What happens in this case, if you do the math on that and do the coincidence measurement, you will see that periodicity doubles. If you just detect 1 single photon here, it becomes like it's a normal Mach-Zehnder interferometer. If instead of the 1 single detection, you do 2 detectors and coincidences, you see the periodicity increases 2 times. And the slope, of course, here is 2 times higher. You have 2 times better resolution. Well, you will say, okay, 2 is good. Let's make 5, 10. Well, try to do that. Again, as I said, it's a big, big problem how to make this state, to introduce it and make sure it's like n here, nothing there, and vice versa. And the main problem is non-selectivity of the beam splitters for the splitting of particular state. That's the issue. For 2 exists, for more, not really. Okay, so that's basically, this is a slide from one of the John Dowling's presentations. He was a very, very old friend of mine. He was at Louisiana State University. And that was a symbol of his research lab, and that's what we will show him basically, that with N002, the increase is lambda divided by, instead of the period of lambda, you will have lambda divided by n in there. He was theoretical, he was theoretician. Okay? With this, I'd like just to switch a little bit to show you something different. We all already appreciated the role of beam splitters, right? On many, many occasions, because this is one of the central elements of quantum optics everywhere. So what is a beam splitter is? As you can already seen, so 2 in, 1, 2, 3, 4 out. In principle, from the scattering theory, it's a 4-mode device. 1, 2, 3, 4. But transformation is only 2 by 2. So there's a mismatch between the potential capacity and the execution. What the problem? The problem is with beam splitter is directionally biased. What does mean directionally biased? If I come from these 2 sides and go out from these 2, I cannot go back. I cannot link the outgoing modes with the input. That's the reason why instead of 4 by 4, I have 2 by 2 only. Okay? And we all know that this splitter gives you nice Hadamard transformation. That's why it's so popular in quantum information processing for many, many things. So for quantum walks, the only problem is if you want to cover more opportunities, you have to put more and more beam splitters. Your system is growing very rapidly. From the other side, again, Conventional effect, we already seen what it is. So beam splitter, when you put 1,1 state inside, it's 1 in one mode, 1 in another, correlated to photon state, not entangled, just correlated between two modes. So these two options are gone, only these two left, 2, 0, 0, 2. This is the result of the interference and cancellation of these two terms. Only these two terms survive and gives you Conventional bit. The main point, and that's what we kind of got question at some point ago. If our conventional beam splitter is a 4-port device but biased, gives you 2 by 2 matrix connection between fields, can we design something with the same 4 modes but will give us 4 by 4 matrix? Scattering matrix. So basically this device should be able to take any field to any other field. So you come from 1, you can go to 2, 3, 4, or backwards to 1. Reverse. And the same symmetrically for everything. And that's exactly the whole idea, to have a directionally unbiased 4-port. This 4-port could be different. The one interesting combination is the Grover coil. Love Grover, remember I told you about the Grover search algorithm. He designed a particular type of matrix that basically the quantum walk is you send the photon and it experiences scattering center, gets scattered, and then again, and your energy kind of walks through the system. And he calculated what kind of scattering centers would help you to reach the far point faster. And he came up with his structure of the matrix that will do that, where D is a dimensionality. It could be 2, 3, 4, 5, 6, 7, whatever. So we started with 3. When you have D equal 3, that's a matrix. In fact, that's where we originally started, 3-dimensional direction and unbiased device. Oh, it looks like this combination. And we even did experiment to show that it's experimentally doable to make this device. However, while working on that, we discovered, okay, if we can do 3, can you do 4? And basically, this is the review that shows this. So when we get to the 4, we were kind of impressed by the symmetry of 4-dimensional Grover matrix. You see the symmetry? All ones and all the diagonals have minus. So if you come from 1 and go back from 1, you get pi phase shift. But if you go from 1 to 2, 3, and 4, it's equal probability. So what is this? So this is just kind of like bulk implementation of that. So these are beam splitters, these are mirrors, and they are phase shifters. So basically, when photon comes in, what it can do? It can go here, and after the first trip here, it has a 50% chance to leave. Or it can go inside back, and again here, or back here. So photon walks and just goes around, and you can show that after maximum 10 interactions between beam splitters, of the photon with beam splitters, it's gone because at every time it has 50% chance to leave. After maximum 10 interactions, it's gone, 99%. So you have to make sure that within these 10 interactions, you don't know where the photon is inside, or in other words, you preserve the coherence of this interaction. Then you can treat it as the scattering element. Basically, scattering element with 4 modes, and this is the matrix associated with the scattering element. It's very easy to do basically because think about this. Even in the bulk implementation, if this is about between beam splitters like 30 centimeters, it's 1 nanosecond. So 10 times 1 nanosecond, it's 10 nanoseconds. You have to preserve your coherence lengths over 10 nanoseconds. It's not a big deal. But when you start shrinking your device, make it smaller, it becomes even easier, basically. Okay, so you have a scattering element, this Grover coin, 1, 2, 3, 4, and this is the matrix. So immediately you would think, oh, it gives me more flexibility, more access to more degrees of freedom. Of course. Let's talk about one specific, and there are lots of things you can do that in quantum optics. I'll show you something that you can do. We call it quantum inspired. Basically, there's what I will show you. You can do with conventional coherent classical state, but the idea came from the what we did in the quantum domain. So. Conventional Michelson interferometer. This is the Michelson interferometer. Everybody knows that, right? So what Michelson interferometer does, it has 2 arms with 2 mirrors and basically 2 phase shifts can go there. And when you do the interferogram inside, it depends on the phi 1 and phi 2. How it depends? It depends linearly. Phi 1 minus phi 2, or like you can make phi 1 plus phi 2. It's a linear function. So you change one of them and you can trace this shape. If you can change phi 2, you just linearly shift this curve. You don't change the any periodicity of this curve. The red one. Basically, that's what conventional Michelson. So the only way to improve the resolution of conventional Michelson is to change the frequency of the light inside. If you change the frequency, make it shorter wavelengths, then you can increase the sensitivity. You cannot increase sensitivity by playing with these 2 phases because they are connected through the linear relationship. Well, let's do this. Let's throw the beam splitter away, replace this beam splitter with the Grover core. Still the same topology, absolutely the same as Michelson interferometer, but now it's a Grover core that I've shown you. Basically, if your photon, so source comes here, this is interferometer, detector, it's a standard configuration how you use the interferometry. And what happens is if a photon comes out here, get reflected back, it can go inside, but it also has probability, remember, to come back again second time with a negative phase shift and so on. It's a very weak, not high quality cavity here and here start to show up. And when you do the account of all the possibilities here and you calculate the intensity distribution, you come up to a very interesting conclusion. If, by any chance, your phi 1, like phi 1 here, is 1 pi. This is units in pi radii. It's 0, pi, 2 pi. If it's pi, right here, so then, phi 2 is our control. Let's say green. Green is a conventional Michelson interferometer. If phi 2 equals pi, you see it's the resolution of this, it's even worse than the conventional Michelson. You see this curve is more fat than the other one. If blue, phi 2 is pi over 4, you see the curve becomes like this. If phi 2 is pi over 8, then this black curve right here, and you see how sharp is here, but the most sharp slope is right there, right here on this side. So phi 2, and this is your scanning phase. So if I select phi 2, for example, to be pi, I'm on this curve. So if I scan phi 1, this is slope that gives me resolution. If I go and pick up the sharpest one right here, what I can do, I can compare delta phi 1. For example, phi 1 changes. if it changes right, and the change over phi 1 is this small change right here. If I'm sitting on this green curve of conventional Michelson interferometer, then that's the size of the intensity modulation I would have. Because you see, it's transmission. Transmission is how much intensity, that's what you detected as your detector. But if I go on this slope, it becomes dramatically greater here. So the same width here generates substantially bigger magnitude of this change. So which means it's like you amplify, because the slope is great. That's what it is. So this delta phi are the same, but this results in this intensity modulation. This one is like 10, 15 times bigger than that. That's an outcome of the of this approach. You replace this beam splitter with the Grover coin, and you increase substantially the sensitivity of conventional interferometry in this case. What else you can do with this Grover coin? You can do other interesting things. Conventional Hongo-Mandel effect, 2 in, 2 out, but only one option. You don't have any other options here, just here and there, that's all. With our system, well, this is the Grover multiport. We take one state, we introduce it inside this multiport using the circulators basically to come in, and when it goes back, it goes this way. Because circulator is a device that you come from here, you go here. When you go back, you just go through the other one. What happens is you come in this multiport, and because of the symmetry, this 4x4 symmetry of this multiport, is divided in 2 sides. It's either going through or going back, probability amplitude, and there is no cross terms. It just the sum of these cross terms, or they also got canceled, the same as before in Hongo-Mandel. With one caveat, now this is all at the level of the probability amplitudes, but then if we put beam splitter here, what do we have? We have 1, 2, 3, 4 modes out. The final result is, and these 2 photon amplitudes are converted in 2 here, nothing there, or nothing here, 2 0, or 2 here, nothing there. So 2 0 0 2 between E0 and F1. Like E0 and F1. That's when you do nothing. If I change just one phase here linearly, just a simple phase, I can do it here and there. If I change phase here and here, I can move the this state between this mode and that mode. If I change it right here, it will do this and this. So we get a high dimensional Hongo-Mandel effect. Now we have 4 different combinations where we can realize Hongo-Mandel effect. And then we realize, oh, it's a nice switch. Because you know, this state is non-classical state. It's not really entangled in terms of that you can use it because 0 has no energy inside there as we discussed, but it's still non-classical state. So, but we can control by just changing the phases, and it's really easy these days. Phase changes, just if it's a waveguide, you put the electrode, apply the electric field, and you should have a phase shift. So, okay, Hongo-Mandel in higher dimensions. What it can be good for? Well, we ask ourselves if we can do this switch between 4 different combinations of correlated state, 1-1 state, which is not entangled, but 1-1, correlated. Can we just add superposition, make it entangled state, and can we try to switch entangled state? And the answer is yes. We have shown that you can do that, and entangled state switching is very important for the networks when you try to connect quantum computers, as I mentioned before. So you have to do the entangled state connection. Well, it's a long story short, so you can put entangled states here, this. Depending on which phases you initiate, you can have out of these 2, now you have these 2 entangled, or that one and that one. So you basically distribute this entanglement here to different ports. And also, you can basically have the, like if you have a network of such systems, like this is one node, second, and so on, different users. So let's imagine 1 and 2, the photons are entangled. We introduce it at this point. We introduce them here in the first node, and then we start moving them around, following all these rules of the phase shifts, linear phase shifts. We don't, because remember, the linear phase shifts, they do not alter the quantumness of the state. It's linear. Okay, so instead of when 1 and 2 entangled here, we can make sure that they go, and 1 will go to this node, 2 will go to that node, but these 2 distant nodes still will be entangled. It's a distribution of the entanglement in the network. Well, how to make it? Theory looks great. It always goes ahead of the experiment. So how to make it is, this is the kind of like the idea in terms of the block diagram. We tried it with 3 by 3 originally on the optical table. It was extremely hard. The only reason we were able to complete our experiment because I had a student who was Japanese. And they are very patient and very meticulous to align these interferometers. It's very, very, very hard. And that was the first time we realized, yeah, we need to shrink it down to make it integrated. Because when it's small and all together, it's much more stable. And then the question was how to do that. Because all quantum optics miniaturization today goes through this principle. We have a beam splitter, so it will be coupled waveguides. You have a mirror, it will be distributed Bragg mirror in there. Phase shift is just an electrode next to the waveguide. That would be your phase shift. If you try to do this, it's still pretty big and very, very difficult to do. We're going in that direction until I discovered by accident, Yelena Vukovic from Stanford came to discuss at the colloquium how they use technology that is called the inverse design to build photonic devices for telecom. You know how you do the kind of WDM filters or switches in telecom. There is a bunch of fibers, filters, and the filter tells you which frequency goes this way or that way, wavelengths. So they decided, okay, let's do it differently. On the chip, I have input waveguide where everything comes, signal comes, and now I need to have like 5 channels. Lambda 1 goes here, lambda 2 here, lambda 3, lambda 4, lambda 5. What kind of scattering environment can deliver that? Okay, they set up boundary conditions. What's on the input, what's on the output, and inverse design means they just calculate what scattering device, what position of materials like silicon or silicon nitride can deliver these boundary conditions. And it's kind of, well, the first thing is there's no unique solution exists. It's just some distribution of silicon or silicon nitride, but it satisfies the boundary conditions. So it looks sometimes ugly. You don't know what's inside, really kind of strange. But if you put light here, then it goes where you want to do. And this was for light distribution, and this is intensity. And I asked her, okay, that's great, but in quantum mechanics, our boundary condition is different. It's in amplitude and phase. So you have more boundary conditions than in classical. She said, yeah, it's possible, you just have to calculate longer. The mathematical problem of inversing the matrices with more boundary conditions is harder, but it's possible. And that's basically what my students are doing right now. This is the basically, this is the calculated distribution of, we do this in the titanium dioxide, something of the in the visible spectral range. So these are waveguides. This is the really scattering element, and this is the simulation still. So input 1, so the light comes from input 1, and you see it can go back here, and it can go back. And input comes from input 3 and so on. It's pretty equal right now, so it's getting close to be equally weighted on all pores, because remember, equally 1, 1, 1, 1 everywhere means intensity is the same, amplitude should be the same, but also the phase as well has to be negative when you go backwards. So we start doing this. It's only electron beam lithography can do that. This is basically the size of the whole thing is here about a micron. So it's sub-micron resolution lithography, and that's what is the work in progress. Hopefully we can do it and start showing all these devices we built in practice. But right now it's still here. With this I would like to finish. Thank you very much for your attention. Sorry for keeping you so long. And thank you.